Imagine you're an engineer designing a jet engine. You need materials that can handle extreme heat. We're talking temperatures over 1,000 degrees, while staying incredibly strong and lightweight. For decades, we've used titanium aluminum alloys for exactly this purpose. They're the workhorses of aerospace engineering. But here's the challenge. What if I told you that until now, scientists couldn't accurately predict how these materials would behave at different temperatures and compositions without running expensive, time-consuming experiments? And what if artificial intelligence could change all of that? So here's what's fascinating. Researchers at Mississippi State University and Los Alamos National Laboratory just created something remarkable: an artificial neural network that learned to predict how titanium aluminum alloys behave by studying nearly 3 million atomic environments. Think of it like teaching a computer to understand materials the way a master chef understands flavors. Now, you might be wondering, why does this matter? Well, these alloys don't just sit still, they transform. At lower temperatures, titanium arranges its atoms in one pattern called the alpha phase. Imagine atoms stacked like oranges at a grocery store. Crank up the heat, and boom, they rearrange into a completely different structure called the beta phase. Add aluminum into the mix, and you get even more phases with exotic names like D019. Each of these phases has different properties. Some are better at resisting deformation under stress. Others are easier to shape and manufacture. The trick is knowing exactly when and where these transformations happen, so you can design the perfect material for your application. Now, traditionally, scientists had two options. Option 1. Use quantum mechanics calculations. Super accurate, but painfully slow, like watching paint dry in slow motion. Option 2. Use simplified mathematical formulas. Much faster, but they miss crucial details, especially when it comes to predicting these phase changes. This is where the neural network comes in. The team trained it on quantum mechanical data, essentially giving it the best of both worlds. The result? A tool that's as accurate as quantum mechanics, but runs 1,000 times faster. It's like having a superpower. And here's the really cool part. This neural network correctly predicts something called the phase diagram. It's basically a map that shows which phase exists at any given temperature and aluminum content. Previous computer models failed at this. They either couldn't predict the phase boundaries at all, or they got the trends backwards. This new approach nailed it. What does this mean practically? Well, instead of spending months in a lab trial and error testing different compositions, engineers can now run virtual experiments on their computers. Want to know if adding 5% more aluminum will improve creep resistance? The neural network can tell you in seconds. But let's zoom out for a moment. This isn't just about titanium and aluminum. This represents a fundamental shift in how we design materials. We're entering an era where artificial intelligence can explore vast design spaces, millions of possible compositions and processing conditions, to find optimal solutions that humans might never discover on their own. Think about it. The next generation of jet engines, hypersonic vehicles, or even fusion reactors could be made from materials designed by AI, predicted atom by atom, before anyone even sets foot in a laboratory. Of course, we're still in the early days. This neural network works beautifully up to about 30% aluminum, but there's a whole universe of alloys out there with 3, 4, or even more elements. Each additional element exponentially increases the complexity. But that's the nature of cutting-edge research, right? Every breakthrough opens new doors while revealing new challenges. So here's my question for you. If artificial intelligence can now predict material behavior at the atomic level, what other grand challenges in science and engineering could we tackle with this approach? Could we design better batteries, stronger, lighter construction materials, maybe even new medicines? I'd love to hear your thoughts. Drop a comment below and let's discuss. And if you enjoyed this deep dive into the world of computational materials science, hit that like button and subscribe to Engisphere. We've got more mind-bending science coming your way. Until next time, stay curious, stay innovative, and keep pushing the boundaries of what's possible.